I've run from the ice chamber where I was to the ocean. Welcome to our ocean session. I'm here with Hermione.
Hi, Susie.
We're talking all about the importance of the oceans. Now, we know well that the oceans are a great sink for carbon dioxide, and indeed, as we've pumped more carbon dioxide into the atmosphere, the ocean has done a great job of absorbing much of that. But that can't go on forever. And so we're going to be talking today a little bit about reducing the amount of carbon dioxide that we emit, and of course the value of the oceans more broadly. Please put questions in so that we can ask people those questions. Yes, Hermione has the iPad right here. We're ready. You can see a question box on the right-hand side of your screen. Do pop in any questions that that come up in your classrooms. We'll do our best to get through as many of those questions as we can. What's coming up in this session, Hermione?
Well, Susie, we have got a lot going on. Soon we're going to be going live to the National Oceanography Centre, and we're going to be hearing from a robotic systems engineer. I believe you might know Matt Kingsley.
I do, yes.
He's giving us a 2023 update on probably one of the most famous underwater robots, Boaty McBoatface. So we're going to be hearing what Boaty's been doing recently. And then we're going to be meeting up and hearing from somebody who I'm really keen to meet. This is somebody who has set up a company that's developed a really clever biodegradable plastic made from seaweed. And his company is still the UK's only winner of the £1 million Earthshot Prize. And Susie, I really want to know how you get your hands on one of those prizes. What do you have to do to get that?
Me too, sounds great. But before we go down there, we are going to join Lauren, Dr. Lauren Bierman and Dr. Daniel Cluley, who are in the Plymouth Marine Laboratory to tell us a little bit about marine ecosystems. Are you there, Lauren and Dan? Hi there, can you hear us?
Yes, we're here, hi.
Fantastic, great, over to you.
Well, hi, so thank you for the introduction. I'm Dr. Lauren Bierman, and I'm a marine remote sensing lecturer and researcher based at the University of Plymouth.
And I'm Dr. Dan Cluley. I'm a research software engineer based at Plymouth Marine Laboratory, which is where we are today.
And now, if you'll excuse us, we actually have to dash across town back to the university campus, where we will be using the coastal basin to demonstrate the scale of the problem of marine plastic pollution. Let's go. Agree that plastics don't belong in the sea. They can cause harm to marine animals if the animals accidentally eat the plastics or become entangled in them. And plastics are actually often made from fossil fuels like oil, gas, and coal, so they can leach harmful chemicals into the water. And bigger plastics often break down into smaller and smaller pieces, making it harder and harder to remove them. Plus, plastics are horrible in nature. It can make us feel sad or frustrated when we see plastic littering our beaches or floating in the water. So if we all agree on this, why is approximately 14 million tons of discarded plastic still ending up in our oceans every single year?
When your grandparents were born, plastics barely existed in the shops and in their homes. They only really began to get mass-produced about 50 to 60 years ago, when petrochemical companies started turning fossil fuels into consumer products. Plastics made life easier. They're cheap to make, made cars and planes lighter so they need less fuel, and they proved to be incredibly durable. So durable, in fact, that they last practically forever. Your nan's first plastic toothbrush may still exist as a toothbrush today, probably buried deep inside a rubbish dump or a landfill, or maybe it got burnt. Maybe, however, it got washed into a river, and that river washed into the sea.
Yeah, and approximately 8 billion tons of plastic have been produced since those early days. 8 billion? That's approximately the same number of people alive on the planet today. 8 billion tons of plastic, 8 billion people. So if we think about it like that, every person alive right now basically inherits a ton of plastic. Now, Dan and I did some super rough calculations, and we reckon that a ton of plastic equates to about 115 big bins of plastic per person.
And this is what 7 bin bags of plastic looks like. And this small patch of plastic would be visible in a single pixel or data point in optical imagery collected by the multispectral instrument on board the Sentinel-2 satellite.
Don't worry, I'll explain what Dan means. So thanks to the European Union's Copernicus program, the satellite data that Dan and I use to search for plastics on the ocean's surface are available freely to anyone in the world who wants to use this data. Now, it does take a bit of skill to know how to make the most of these data. And in fact, that's what I teach at this university. I teach students how to make the most of satellite data. But one of the first key lessons that I actually share with them is that while there are many satellites in polar orbit collecting loads of really useful Earth observation data, the most important step is probably selecting the best type of data for the work that you specifically want to do.
So, to successfully detect floating plastics and other material on the surface of the oceans, we specifically need satellite data, which is acquired over water and at what we would consider high spatial resolutions.
That's right. Now, for us, high spatial resolution is about 10 meters by 10 meters. So, if you walked or ran in about 10 steps forward, and then turned, and then did 10 big steps to the right, and then turned, and basically made a big square, this is the size of 1 pixel, or data point. Now, the European Space Agency's Sentinel-2A and 2B satellites work together as a constellation to collect data in the form of these pixels, or data points, 1,000 at a time, at 10 by 10 meter spatial resolutions, over coastal waters all over the world every 2 to 5 days. And the type of data that they collect is optical.
So what does Lauren mean by optical data? So the Sentinel-2 satellites both carry these multispectral instruments that are essentially their eyes. So like many of us, they see the world in colour, including blue, green and red. But unlike any of us, they can also see into parts of the electromagnetic spectrum that we cannot, meaning they can collect imagery outside the visible spectrum of light.
Yeah, exactly. And in other words, the multispectral instrument can collect slices of light all along the electromagnetic spectrum from, as Dan said, in the visible that our eyes can see, into the near-infrared and the shortwave infrared. And this is super important for our work because when it comes to detecting floating objects on the ocean's surface, water becomes increasingly efficient at absorbing light in the red edge, the near-infrared and the shortwave infrared. So, if we look at the ocean using only near-infrared light collected by the multispectral instrument aboard the Sentinel-2 satellites, the water is going to look completely black because it has absorbed all of the light in those wavelengths.
Anything floating on the surface of the water, however, will appear bright and reflective by comparison. In the near-infrared bands of the electromagnetic spectrum, boats out on the water on a nice sunny day can look like bright stars against a night sky.
Speaking of a nice sunny day, reviewing optical data collected by the Sentinel-2 satellites is pretty straightforward when the data are collected under those lovely meteorological conditions. So just like our eyes, the multispectral instrument is passive. So it means like us, it needs light to see. Of course, in this case, we're talking about sunlight. The satellite sensors can't observe the Earth's surface at night or even through cloud. So if you're looking for floating materials on an overcast day, even if you know for a fact that they were there, you're not going to be able to see them through the cloud using Sentinel-2. So far, we need satellite data that's freely available, collected at high spatial resolution, optical like our eyes, but also including the near-infrared and shortwave infrared, and collected during the day without a lot of cloud in the way. So that feels like a lot, and it can be, but there's more. Unfortunately, we're not yet at a stage where we can detect individual pieces of floating materials, even big pieces, macroplastics that we can see and hold like this.
In coastal waters, the ocean helps with this by naturally grouping or aggregating materials into patches big enough to fill at least half of one of those 10 by 10 meter pixels. Especially in the near-infrared wavelengths of light, we're able to detect these patches on a sub-pixel scales. And because natural materials look so unique and so different to plastics, we can start to use this information to train a computer program to help us classify what's dominant inside a pixel. Natural materials include seaweed, sea foam, driftwood, and even the seawater itself. Anthropogenic or man-made materials floating on the ocean are most often plastics.
Now, I was lucky enough to be sharing an office with Dan while I was detecting pixels filled with floating materials that I just couldn't identify as anything natural. You remember?
Yeah.
And then I was trying to find a way to show other people in the scientific community that it was probably possible to detect plastics in the optical data collected by the Sentinel-2 satellites. And it was Dan who kindly taught me how to teach a computer program to help my work more accurate and more reproducible, even though in the beginning we had really little training data to start with.
Yeah. So machine learning is a subset of AI that's becoming more commonly used for work like Lauren just described. So she was spending up to half a day manually processing one satellite image at a time. And this is where machine learning really belongs, helping skilled people like Lauren do their work quicker, more efficiently, and more accurately. So machine learning needs data to learn from. The more complicated the algorithm, the more data it needs. For this example, we chose a really simple model, a naive Bayesian classifier, as it's able to work with very small data sets. And when Laura and I started working together, she only had 9 pixels of plastic to start with. Today we have a lot more training data to work with, and we can use increasingly complex machine learning models to classify marine plastics. This is helping us and others to detect and classify floating debris patches all over the world. But plastic pollution is only one of many marine stressors. We're also using machine learning to improve a range of other marine applications, including anomaly detection, tracking things like internal waves and oil spills in the satellite, radar data collected by Sentinel-1, and monitoring climate scale events like El Nino development in sea surface temperature data.
Yeah, and it sounds really serious, but my students who are brand new to marine remote sensing and also brand new to machine learning, they're already combining Sentinel-2 data that we've just talked about, including radar data from Sentinel-1 with machine learning to count the number of boats stuck in a traffic jam.
So as marine scientists, whether we're looking at our oceans from space, doing analysis using machine learning, or collecting measurements from a boat, the thing that ties all of us together is a desire to better understand what we're seeing or measuring in the marine environment, and a motivation to protect something that we love.
Indeed. So if you have that same curiosity to know more about how our oceans work, you're already well qualified to start your own journey as a marine researcher.
Play to both of you for diving in at the end. I wondered if that was going to happen. We're so impressed.
Yeah.
All in the name of science. Thank you. And that was a really wonderful introduction as well to your science. The first question that came to mind actually was about using machine learning algorithms for detecting features. And you talked a lot about detecting plastics in the ocean and other features, and we've heard a bit about icebergs in the past as well. I wondered if you could talk a bit more about marine mammals. Can we track marine mammals using Earth observation techniques?
There is the potential for using extremely high resolution data collected by commercial satellites, satellites called WorldView, for example. They collect data. So when Dan and I talk about high spatial resolution, we said 10 by 10 meters. These are satellites that can collect data on sub-meter scales, so really, really high resolution. And there has been work progressed by the British Antarctic Survey, I believe, where they have used this very high resolution data to track whales. But a lot of the time, actually, we put instruments on different types of marine animals so we can track them using satellite tags. And we can then look at their distribution patterns relative to what's happening in the biology and the physics, which we can also measure from satellite.
Okay.
That is amazing.
That's
I love
great.
that.
Now, I'm tracking all your questions coming in. Thanks so much. Definitely keep them coming. There's a couple of questions here, Dan and Lauren, all about sort of when you can see the plastic from the satellite imagery, how do you know how deep it is? And then how do you work out how much it's going to weigh? What can you tell about that plastic?
So this is something that we're not yet able to do. At this stage, it's a bit binary. It's either there or it's not, but we know it's at the surface and in fact emerged from the surface because it's reflective in the near infrared wavelengths. So we already know that even if it's just a few centimeters below the surface of the water, it's not detectable by satellite using this method. And in terms of mass and in terms of concentration, we're not yet at a stage, unfortunately, where we can even identify individual types of plastics or dominant types of plastics within the multispectral data collected by the Sentinel-2 satellites. This work is being progressed, of course, but this is not something that we've been able to successfully do yet.
Oh, fantastic work moving forwards.
Yeah, work
just
in progress.
One last question for you, because I know we're running out of time, but lots of people have been asking us about the damage that these plastics do to creatures living in the ocean. Perhaps you can tell us a bit more about that.
Yeah, I think we've all seen those really horrible pictures, haven't we?
Yeah.
So plastics tend to be predominantly made from fossil fuels, oil, gas, and coal. And it's not just that they can entangle animals or animals can accidentally eat plastics. It becomes lodged in their stomachs. I mean, if you ate a balloon, please don't eat a balloon. Please don't tell your parents I told you to eat a balloon. But if you did, that would be really bad for your digestive system. And the same is true for any turtle or dolphin or whale or seabird that accidentally does the same thing. Because the plastics can look like food. And if their stomachs become damaged or full of plastics, then, well, really terrible things do happen. And of course, the plastics themselves can leach chemicals. They can entangle animals. I think we've also seen lots of videos where people are freeing animals that have become caught up in the plastics. And even right at the base of the marine food web, at the zooplankton level, so the little critters that basically feed on the phytoplankton that feeds everything else in the marine food web, even they can become damaged by microplastics that we can't even see with our eyes.
Wow, fascinating. So take home message, don't eat balloons. And we really need better high resolution images around the globe to enable us to do better science and move this forwards. Thank you so much for joining us. We really appreciate your time, especially the fact that you dived into the swimming pool for us. Well done.
Thank you for having us.
And thank you again. That's wonderful. Bye for now. We're going to go actually straight now to Matt Kingsland, and he is a friend of ours who we met last year, and we talked a lot about Boaty McBoatface. We're going to go and hear a little clip from what they've been up to over the last year.
Hello, my name is Matthew Kingsland. I'm an engineer working here at the NOC, the UK's National Oceanography Centre. The NOC's job is to operate globally, monitoring the world's oceans and their environmental health. To better monitor the oceans, we develop advanced technology for ocean research, including the Boaty McBoatface submarines. Boaty is an autonomous submarine, meaning nobody goes inside. Instead, when we launch Boaty, we give it a science mission. These missions consist of locations in the ocean that it will visit and what it should monitor when it is there. The data Boaty collects could be anything scientists need to evaluate the marine environment. Boaty measures the water quality, looking at what microbes, chemicals and elements are in the water. It can take water samples for processing back in the lab on shore. And it collects images to look at habitats. What makes Boaty unique is it's capable of very long-range missions, being able to travel 4,000 kilometers before needing to recharge its batteries. That is the equivalent of going from the UK to the south of Spain and back without recharging. By using batteries, we can do environmental science with a very low carbon footprint, rather than the high carbon cost of the equivalent diesel-powered ship. Once launched, depending on the mission, we might not see Boaty again for several months, while it goes off into the ocean and carries out its mission. However, Boaty does phone home every 24 to 48 hours to tell us that it's okay. Since our last update on Boaty's adventures, it has been doing lots of missions up in the very north of Scotland, operating from a town called Lerwick in the Shetland Islands. Boaty has been fitted out with a camera system and has been going out to inspect old, decommissioned oil and gas sites. These sites used to produce oil, which was used for everything, including the petrol for your car. However, as the oil in the well runs out, these sites are no longer needed and have to be decommissioned. We send Boaty out to see what state this old infrastructure is in and how it is affecting the environmental habitat. in the North Sea. We have seen lots of images of marine life, including fish, sponges and other creatures, but we have seen lots of man-made rubbish as well, which has been left behind during our activities there. The data BOTY is collecting will be used to inform us on how to better clean up the ocean of things we as humans have left behind, and how to monitor old oil and gas infrastructure. There are hundreds of oil and gas rigs in the North Sea which are due to be decommissioned over the next decade. We need to remove them safely as we move towards environmentally friendly energy sources, such as wind turbines. As that equipment is decommissioned, we need to make sure it's all removed and no damage is done to the environment in the process. BOTY will be out there doing that monitoring. The other mission that BOTY has been doing this year is monitoring the UK's coral reefs. Now, when I say coral reefs, most people are surprised to learn that the UK has coral reefs. They are usually more associated with warmer climates, such as the Caribbean or Australia. However, the UK has something called cold water coral, and this coral can be located quite deep in the ocean at several hundred meters. However, this coral is in danger because this coral is so deep in the ocean, it hasn't been known about for very long, meaning we have been fishing and trawling over this coral for hundreds of years. A large amount of this coral has been destroyed and is now rubble on the seabed. In 2022, the UK government banned damaging fishing from 4 of the UK's offshore marine protected areas. However, the goal is to have 40 sites properly protected from damaging human activities. Trawling drags a big net over the seabed, not only collecting the fish, but the coral as well, and other marine life. BOTY will continue to monitor the corals, how they grow, and how they are damaged going forwards. On top of the current missions that BOTY is doing, in 2024, BOTY is doing something different. Its mission in 2024 is to drive from Iceland back to the UK, monitoring how much carbon the ocean is absorbing. The ocean is one of the biggest absorbers of CO2, which is one of the main greenhouse gases. As the ocean absorbs CO2, the side effects is the ocean acidity increases. Lots of animals don't react well to this acidity increase, and we need to go find out what the consequences of our actions are. Thank you for listening today about the adventures of BOTY. We will continue to give you updates in future Protecting Our Planet sessions. But if you want to see anything earlier, please visit our website. And if you have any questions, I would be happy to answer them now. Thank you.
Wonderful. Thank you so much, Matt. And there you are. I hope you can hear us live. This is wonderful. Thanks for joining us again. We really, really appreciate it. I just want to give a quick shout out to anyone in Shetland. If you're in Shetland watching, then please let us know. Type something into the chat. We'd love to have a shout out for all of you. But we've got loads of questions that have come in for Matt. So let's get started.
That's right. Matt, just a quick one here. From the Burgess Hill Girls 8A, they want to know about the batteries on board BOTY. How does the power work? How many batteries does it have?
So we have a couple of different sets of batteries which go in this, but we mostly use rechargeables. So the sort of thing that you will charge up off a mains power supply and then install, and then we send BOTY out and mainly runs off rechargeables. This is because it's incredibly low carbon. If you start using single-use batteries, they have a really high carbon content, which kind of devoids the point of BOTY, which is to help save the planet and produce really low carbon science.
That's fascinating, and maybe something we can all bring back to our own lives about using fewer batteries and trying to use renewables more than batteries. I have a question for you about navigation. So BOTY in the giant ocean is not very big. How do you keep track, and how do you steer and make sure that you're going the right way?
So every 24 hours or so, BOTY comes to the surface, and she phones home and lets us know where BOTY is, and also gets a GPS lock. So very similar to what your phone does. So your phone gets a GPS lock and tells you where you are, so you can navigate with Google Maps and stuff like that. Unfortunately, when BOTY goes under the water, we lose all GPS communications because the water blocks it.
Yep.
So once she goes under the water, we use effectively a compass, but just a very complicated compass. So you get your heading from the compass relative to north, and and then it also looks at kind of the water speed around it using like paddle wheels and things like that to measure speed. So it knows what direction it's going from the compass and how fast it's going from things like paddle wheels and other methods.
Interesting. And so one last quick one on this. You can work out sort of where you are. What about hazards in the ocean? Do you have to worry about bumping into things, or is the ocean so vast that that's unlikely?
So sometimes when we're doing camera surveys and we're going particularly close to the seabed, we put a forward-looking sonar on board, which looks at the seabed in front of the vehicle and tells us if there's any shipwrecks or unknown obstacles coming up. But if we're not so close to the seabed taking images and we're much higher, we generally fly without looking at what's in front of us.
Wow, brave, great.
Wow, there's loads of questions coming in, Matt. I'm just going to try and sum up because lots of people want to know, how fast, how deep, and it just seems like there's so much technology packed into this relatively small autonomous vehicle. You're a systems engineer. How long has it taken to kind of develop all the technology and build Boaty? That's what Dylan wants to know.
So quite a long while. So from design to in water normally takes about 2 to 3 years, depending on whether we're starting from a completely blank sheet. But most of the time, now that we've got Boaty and other submarines, we just iterate on the design. So we do a lot of work just doing small upgrades to slowly improve Boaty's kind of capabilities.
I just have one more actually. Gosh, I keep having questions for you. You're standing there next to Boaty, but I can see other things in the background. Is there more than one Boaty?
So yes, is the simple answer. So we actually own six Boaties exist at the moment, and next year we're going to build 2 more. So you see Boaty in the news quite a lot. It might be a different Boaty that you see each time. It's whichever one's kind of doing the most interesting piece of science is what we try and publicize and let you know about.
Good. I like the idea of shoals of Boaties going around the world. That's wonderful.
Yeah.
Matt, thank you so much for joining us today. We really, really appreciate your time. Thank you again, and we look forward to chatting to you next year to see what
Thanks for
Boaty's
having
been
us.
doing in the meantime. Thank you.
Bye, Matt.
Right, we're going to move on to the last speaker of our session today. And actually, this is an exciting one, isn't it?
Oh, it is.
We are going to be joined by Rodrigo Garcia Gonzalez, who is the co-founder and co-CEO of Notpla. Tell us all about it. And welcome, Rodrigo.
Hello, nice to have me. I'm Rodrigo Garcia. I'm based in London, in Hackney Wick, where we work for a company called Notpla, that stands for Not Plastic. And basically, I'm going to share through a few slides a few of the things that we do. So this gentleman over here, Alexander Parkhurst, invented plastic, which he was not far from here, just across that wall in 1856. And nowadays we use plastic for many different things. Plastic is a wonderful material. It works really well for many different things. It's really light, it's really cheap, it has a lot of barrier properties, but it lasts really long. And this long-lasting kind of like property that plastic has is good in certain contexts, but it's not great when we use it just for a single time, when we use it for single use. We had been hearing before from Plymouth University about some of the effects that this plastic waste could have in different ecosystems, like the seas. We know as well that these plastics, they break down into microplastics and affects marine life. And what we had been doing, initially my background was as an architect. I was collecting these bottles and try to make it into buildings. But quite early on, I understood that it's hard to kind of like solve this problem just with recycling. That's why we started to work on trying to tackle this challenge in the same way that fruits does. If you think on a coconut, it's a natural kind of like packaging that you can eat. And not only you can eat, you will throw the coconut away and new coconut tree will grow. So it's amazing that nature can do that. We as humans, we cannot do that. We throw a plastic bottle, not a plastic bottle tree will grow. But let's see what we can do. That's why we created this product, We call it O because it's the name that people give it when they see it for the first time. They make that sound of surprise. Basically, it's a membrane in the same way that nature uses membranes to be able to kind of like create packaging for different liquids. It's not a technology that we invented. It's a technology that had been there for many years to make things like fake caviar. And what we basically did is a seaweed-based kind of like a material. So we had been getting the seaweed from different parts, different coastlines. Seaweed is a material that grows really fast. Some of the seaweed can grow up to 2 meters a day. So it's one of the fastest organisms on Earth and doesn't need fresh water because they are in the sea, doesn't need fertilizer, doesn't need too much human intervention. Basically, seaweed is a natural material. I don't know if you can see it here on the right-hand side. And you don't need to chemically modify that polymer. So nature knows how to eat it as well. As a human, you can eat it, but if you don't eat it and you throw it away, nature will know how to deal with it in a really, really fast conditions. We started as students just buying products and repackage them and making dinners for friends. It was quite fun. And then from there, we did a crowdfunding campaign where 900 people put from 10 pounds to a few thousands to help us to make machineries that they are the ones that they are behind me. And with these machineries, we have been able to make this product in quite big scale. So we have done things like the London Marathon, where runners, instead of having a plastic bottle, they had in one of the hydration stations this product and they could throw it away or they could eat it. We are working now on energy gel, so making this product as an energy gel alternative, so you don't need to use these plastic sachets. And we can give it different type of shapes. So in this case, for example, this is a pipette, so you can control quite well the dosage. You can still eat it if you want, but it's not necessarily thought to be eaten. And starting to work with different companies, we learn about more places where plastic is. One of the places that we didn't know that plastic was present is inside of takeaway boxes. Takeaway boxes, even if they look that they are cardboard, they contain these kind of like what is called plastics or forever chemicals that make it this material quite hard to recycle, really nasty for human health. And basically, they ask us, can you put the same seaweed into this cardboard material to make takeaway boxes? And it's something that we have been doing now at quite big a scale. So we use a factory that used to make stamps to coat this seaweed into paper. And then we are able to kind of like basically kind of like make this product at scale. We take the seaweed, this is Laminaria digitata, we clean it, then we apply it at quite high scales, and then we are able to distribute these through different channels, like this at the moment used in stadiums, is used by big takeaway delivery companies, is used in different canteens, and I think that has been one of the products that we have been able to do at really, really big scale. This was the final of the UEFA, but we have been doing as well the final of the Champions League, and we're in different stadiums like Tottenham or Aston Villa, which is quite exciting. And in that case, you can recycle the paper or you can kind of like recycle the box. We have been able as well to do this with a few more supporters. So as we mentioned, we won the Earthshot Prize, and Prince William have been helping us as well to communicate and to spread out this product across different potential users. Some of the products as well that we are working on that they are not ready yet, but we are keep pushing is making this into a flexible material that can be used in different type of contexts to substitute flexible films of packaging to make things like pasta or noodles or coffee. And sometimes we can add something else that plastic cannot do. For example, in this case, the flexible packaging, the film has sugar. So if you want the coffee with sugar, you can solubilize it. We are working at the moment in the problem of the detergents. At the moment are using this soluble film that comes from petroleum as well. So it creates quite a lot of challenges. And yeah, it's an industrial process that we need to get into to be able to have a global impact at the scale. With the seaweed, we are using this 20% of the seaweed that is this extract that we use for this type of products. For the rest of the plant, the rest of the fiber, we have been using it to make paper. So we can make now seaweed paper that we use it on different types of applications. And at the moment as well, we are pelletizing that seaweed in order to be able to make injection molding materials, that is hard materials. And yeah, that has been quite exciting journey as well, to use the existing machineries that they are used to make plastic to make other type of materials, like in this case is seaweed. we measure our impact of how many single-use plastic we replace. This year, we expect to replace more than 5 million single-use plastic. And as we mentioned, we were quite honored to win this kind of like quite well-recognized award like the Earthshot Prize on the category of Build a Waste-Free World. So I think that's all I wanted to share with you. I'm super happy to take a few questions as well.
Thank you so much. This is fascinating. I have one question for you to start with though, which is that you showed this being made as something like, could contain your coffee and you pop it into some hot water. What does this taste like? Because I'm quite fussy about my coffee.
Yeah, so it doesn't have any taste. We remove all the taste. So like the part that has the taste is the fiber, and we can remove that. That's not a problem. We can add taste. So like that's an exciting opportunity. So you can kind of like, for example, we have done things like drinks where we can add on flavors on the membrane. So you can combine your soda with a specific type of flavor. Or as we mentioned, like we can add a certain kind of like fragrance, or sometimes we add even lemon peel, for example, in our skin. So it tastes like lemon. So it's playing a bit like fruits. Not necessarily you need to eat the peel, right? But sometimes the peel or the skin of a fruit adds certain flavor. So you don't need necessarily to eat all the skins of fruit. So you can choose depending on the occasion. So for example, on the cases of pipettes, in this case you don't need to eat it. You could eat it if you want. So in this case, you can make a little demo. But like as we were mentioning, it's a product that you can control a bit, like how much olive oil you can put in the salad. Again, you don't need to eat it, but you can potentially eat it, and that's a bit the magic of it, and that's what nature as well does.
Oh, wonderful, great.
Okay, now we're not going to have time for all of your questions, I'm afraid, but one thing that's coming up is what's stopping the transition to us using these biodegradable plastics, Rodrigo? Is the £1 million you got from the Earthshot Prize, is that enough to kind of mean that we can use this all over the world, or is it all about sort of money investment? What's holding us back?
Yeah, so we know that plastic had been on the rise for many years, and there had been a lot of investment put into it, and at the moment as well, it seems crazy, but we are subsidizing quite a lot of like fossil fuels and plastics into the current economy. It's a material that is really well optimized, and it's quite hard to compete in terms of different type of parameters, for example, price or properties. What we propose is that we can go step by step, and starting with applications that they are quite probably small, if that makes sense, if you can compare it with the big problem of plastic, like marathons, for example, or stadiums or energy gels. But at the same time, is the first step to move towards that race that we have at the moment anti-plastic. We are working on all the properties to be able to get it ready. For example, now we are trying to solve the challenge of like making cutlery that's not made out of plastic, but it's still work in progress. At the moment, you can see like the cutlery is still quite flexible, so it's not like working yet. So it works well sometimes for magic tricks, but like doesn't work for certain applications. So we still need to kind of like bring on board quite a lot of scientists, researchers, chemists, engineers to work together on this challenge that we have, to be able to make things that are still natural, so still biodegradable. You won't have the ability to keep them for really, really long time as plastic does, because you will compromise on biodegradability. But we believe for certain applications that normally is small volumes and short-term consumptions, we have something to say with natural materials.
That is wonderful. So if you are listening to this thinking this is a problem I want to get involved in and I want to help solve, then follow Rodrigo's example. Thank you so much, Rodrigo, for inviting us, for coming and joining us this afternoon. We really, really appreciate your time. Thank you so much.
Yeah. Goodbye, Rodrigo. Well, that's just wraps up this session, Susie. Goodbye. If you are looking for the primary ice and ocean session, which is about to start, use the separate link that you should see at the top of your screen, or go to the POP23 microsite and follow the link in. You'll be meeting up with my colleague, Chris. That's going to be a really exciting session for primary learners. Susie, where are you going?
I am heading to the forest, actually, from the oceans to the forest. But before I make a quick dash, I just want to remind you that if you want a climate ambassador to come to your school, talk about climate change and work through some activities, you can request that. And there's a link that you'll see in the chat for your school to be able to request that. So please do go ahead if you're interested in that. In the meantime, our hashtag is POP23 and we want to hear what you're doing. So if you are watching as a school today, or maybe your class is watching, maybe you have some activities, then please do get in touch with us and let us know that you can @Ezero_UK, and we'd love to hear what you're up to. Okay, I'm going to make a run for the forest.
Thanks, Susie. Bye for now.
Thank you.